If you need the area to the right, you find the area to the left, you subtract it from 1. You never subtract 1 from the z-scores. You never subtract the z-scores. You only subtract your areas, your probabilities. So in this case, it says if your z-score, I want the area to the right, it points to the right, greater than negative 2.10. So here's your negative, your zero's in the middle. You want the area to the right. When you look this up, you get this area to the left. And using a sketch is helpful because if you notice, you got a big chunk of curve. It's far more than 50%, isn't it? So when you look it up and it's 0.0179, it's got to be more than 50%. So therefore, you subtract it from 1. It's got to be the larger number here. B says I want the area to the left. And look how far up this is. That's most of your curve. So that number had to be large. And when you looked that up, it was. Because it gives you the area to the left. The area in between two z-scores says take your z-scores, find your areas, and subtract them. This is the in-between. It falls exactly, z is between these two. What happens when you do this is when you look up negative 2.33, you get this area. When you look up positive 2.33, you get all this area. So do you see where your overlap is? Your overlap is right there. You want the one left in the middle. So therefore, if you subtract this guy out of there, you will be left with what's in the middle. So you subtract your areas, not your z-scores. And D is an OR. And an OR says you're going to add them. If they're mutually exclusive, meaning they can only be one or the other, in this case, yes, it can only be this way or this way. There's no overlap. You find both your z-scores and you add them. What's unique here is this z-score of negative 1.75 is to the left. This one is to the right. So you have to find negative 0.75, which is still on the left side of 0. Take that z-score and subtract it from 1. And then you can add them. Even when you add them, they should never come out greater than 1. Your total area under the curve is 1. Make sense? Yes? If it doesn't, stop me. This is for you. Okay. I know a couple of you had a little trouble going back, but this is really going back to your basic z-score stuff. It's a great 2-point question, multiple choice. Find the normal probability. This is your area under the curve. This time, you are given an x value. You have to take your x value, use your z-score formula. If your mean, here's your sketch. Your mean is 5.5. Your numbers are 5.36 and 5.64. You want the area in the middle. So again, you have to find your z-score associated with each one of these x values. This one will be negative for your 5.36. Look up your area. It is the area to the left, and we found that from before. Then do your 5.64. It will be positive. It's on the right-hand side of your 0. Look up this area to the left, and then subtract your areas. Okay? Great 2-point multiple choice question.
How many multiple choice questions are there?
You have to choose 15 out of 18.
And then how many shortest?
We can choose 15?
You choose 15 out of 18. And then the second part is 3 out of 5. And the third part is 1 out of 3. But the 1 out of 3 is your hypothesis. I didn't want to hook it into the 3 out of 6, do that, because I want you to do one hypothesis. So what I'll probably do like your first day is give you the multiple choice and the hypothesis part. Because everybody goes right for the hypothesis. That's what we did last. So that's not going to take you that long.
Oh, that.
Yeah.
Oh, that's gonna be up.
Yes. Yes. And it's just 1 out of 3. So there's one mean, there's one proportion, and like there's one less than, there's one greater than. You know, you can choose which one you want to do. Usually everybody does that one first, so that's why I figured I'll give that out with the multiple choice. You can just get that done and see where you stand from there. The second day, our problems that take a little bit more time. Making a table with a graph, doing a confidence interval, you know, finding your margin of error, doing a confidence interval. There'll be 3 of those types. This is a typical multiple choice problem. You know, something like this, finding a critical value for a cutoff, that's a multiple choice. Definition between samples and populations, that's a great multiple choice. I didn't really make it that hard. Some of them you got to think about. Yes.
That one that you just did, is it just a coincidence that they bring out both 1, 3, 7, 5, or they always?
No, that was a coincidence.
Oh.
That was a coincidence. And in that case, because they were both the same, you really didn't have to look the second one up because you could use this fact and just subtract the 0.0401 from 1 to get 0.9599. If you see that these are the same, right? And here, remember your curve is symmetric. You still want the area to the left, which this is this guy. If you saw that this was now the positive, this is this area over here. So to get the area to the left, you could have subtracted it from 1 rather than look up on your table, or you could just look it up on your table. Use what you know about your curve. Okay? For A through G, we're going to use the following information. In a recent year, 8th grade Washington State Public School students taking a math assessment test had a mean score, pull out your information, and a standard deviation. And how do I know that's the population, not a sample? Because what? No, go ahead.
No, because I was gonna say it's bigger than 30, but that's for someone else.
Yeah, well, we didn't know that at the time, but what gives this away? Washington State public schools, all of them, all of their 8th grade public schools, but that's a good way to do our z-score, Jen, is with the greater than or less than, greater than or equal to 30. So we know this is your population and a standard deviation. And also, it does not say to you the sample has n in it, or standard deviation. So this is your population. The scores range from 0 to 500. That doesn't affect us in our problem. Assume that the scores are normally distributed. Find the probability that a student had a score higher than 315. Set up your probability statement. What is the probability that that x value is greater than 315? Here's your mean, 281. If it helps you, put your standard deviations out here. And add 34.4, add 34 if it helps you. 315 out here, greater than, is that area going to be less than 50 or greater than 50? To this side? Less than 50. So when you look this up, your z-score, if your z-score gives you an area greater than 50, you might want to subtract it from 1. It's a good view to look at. So greater than, all the area you look up is area on the left. Again, guys, watch your parentheses. There's no sample standard deviation here, no sampling, so we don't divide anything by the square root of n. We don't have an n. Population. So use your z-score formula, which you'll have on your test. You'll have your z-score formula. Find your area to the left and subtract it from 1. Find the probability that a student has a score between 250 and 305. 250, 305. In between. One z-score is going to be negative, one z-score is going to be positive. Okay? Find your z-scores, find the areas, and subtract the areas. Don't subtract the z-scores. Yes.
I'm just, this is a long time since I've done this.
Yes.
But when we get the z-score, how do we get the actual value again?
You look it up in your table, table 4. But it's always the area to the left. And in this case, that's exactly what you want. You want the area to the left on both, and then you want to subtract your areas. What percent of the students had a test score that is greater than 250? Percent, don't forget, is your area under the curve, is your probability. So greater than 250, again, here this is. So 250, greater than. That's going to be larger than 50%. Now, you already did a 250. You already found the area to the left. All you have to do is take that area and subtract it from 1. You already found that one in the first part. So just take the area and subtract it from 1. Can everybody do these? Is it coming back to you? You need to know how to do this. We really work with z-scores all year, pretty much. If it was sample ones or population ones, they work exactly the same. If 2,000 students are randomly selected, how many would you expect? You're forecasting, you're predicting to have a score less than 300. Based on your data that's here, less than 300, find your area to the left, and then multiply that by your 2,000 students. If you get a decimal, you'll have to round. Now, generally, on this one, you want to stay within where your bar is. Your bar is over here, like right here. You don't want to go over it because you want to be within that section. So you'll have to round down on this one. And do you remember when we did this? What is the lowest score that would put you in the top 5%? It was the other form of this. So find the x value. I think that will be there too. Is that on your little formula sheet that I gave you? You know the sheet that I gave you with your...
Which one?
You know the ones I gave you with your notes? Is that on that other... This one. Nope. Yeah. This one. Nope. Yeah. It's on your thing right next to your z-score. It's just the transformation of your z-score to find the x value. So remember, the top 5 means you want 5% on the top. When you do inverse norm, be careful. If you look up just the 5, it's going to give you the negative. But you know this is on the right-hand side, it'll be the positive. Otherwise, you can do inverse norm with 1 minus 0.05. That will give you the 95%, which puts you at 1.6445. Don't divide anything by 2 on this one. Use the fact that your curve is symmetric.
Wait, so do we do inverse norm 0.05
Either,
or 1 minus?
Either way. 0.05 is going to give you the negative. But you know it's up here, you just change it to the positive. If you have a hard time with that part of it, then you have to do this part, subtract it from 1, because you are looking for the area to the left. Once you find your z-score, this is your z-score, the rest fits right into your formula. I give you this formula as well. Okay, we did a lot of these. Top 5, top 10, lower 5, lower 10. We did a lot of these. That's finding your x value. What is the lowest score that would still place a student? Oops, we did that one, sorry. What is the highest score that would place a student in the bottom 25%? Bottom 25 means I want 25% of the data right there. Inverse norm, find its z-score, plug in your z-score into your formula. That will give you your x value, your cutoff. Now the next one, we can tell the difference between the population and the sample because now it says in a random sample of 60 students, I have to be able to do something with this. This is my n. What is the probability that the mean score will be greater than 300? I'm still looking greater than 300. Okay, in a sample this time. So instead of using my population one, I have to use the one with my sample. X minus the mean over the standard deviation divided by the square root of n. Now I have a sample, so I use this one. I plug it in and I find my z-score. Now, look, I want the area to the right of this z-score. It's way, way, way down on this corner somewhere, on this edge, somewhere. Your table only goes up to 3.49. Anything to the right of that is negligible. It's approximately 0. We can't say 0 because 0 means it's impossible to happen. And it is possible to happen. So we say approximately 0. If it was less than 300, it would be approximately 100%. It would be my whole curve. Does it make sense? Questions on this one? This is a good one to make sure you know. Taylor, your phone. Guys, put your phones away. In A and B, use the following information. In a survey of adults, 68%, percent, P, proportion, P, I have a P, not a U. Thought the DNA tests for identifying an individual were very reliable. You randomly select N adults, N is 24, and you ask them if he or she thinks that DNA is identifying, or the test for identifying DNA is reliable. They say yes or no, 2 choices. Now, when we do this binomial decision, 2 choices, they can say yes or no, we need to be able to test to make sure this approximates a normal curve. That's why we test. If it doesn't approximate a normal curve, we don't do anything else with it. So we test this to see. If it passes the test, you have a P and a Q. Your Q is 1 minus P. Once we do that, we find the mean, we find the standard deviation. Here's your mean, here's your standard deviation, and your variances without the square root, obviously. Find your mean and your standard deviation. If you can't do it, it's because it didn't pass either of the tests. It has to pass both. Okay. Good? Remember this one? And as soon as you see a percentage, proportion is a P, not a U. Okay.
So if we didn't pass the test, like when you say in a sentence,
It does not approximate a normal curve. We can't use those formulas because it does not approximate a normal curve. I don't know if you remember back to the book, they gave us a series of curves and they had n times p, and as it approached 5, it became more normal. Before that, it was kind of bumpy, like it was way back. It was a little bit bumpy in there, and then all of a sudden, as soon as it was greater than or equal to 5, it approximated a normal curve. So if it doesn't, you just say does not approximate a normal curve. Find the probability that at most 15 people will say yes. So find your probability that at most means that's the most you could have, less than or equal to. Okay? We used our standard deviation, and here's our mean for this. There's our mean. There's our standard deviation. The z-score is exactly the same. We don't need to divide by the square root of n because we've already included that in your n times p times q. You find your z-score and you find your area to the left. If it says probability, it wants the area. Probability, remember, is between 0 and 1. And it's never negative. Good? How many questions were there altogether in this paper? 14 again?
But you crossed
I-
out 14.
I crossed out 14.
Yeah.
Alright. Let's see if we can start your confidence intervals. This probably needs some remembering. Okay, point estimates. When we do a point estimate, it means we don't know enough about your population, so we use your sample to estimate what is going to be the population mean. Point estimate is your sample mean. What is going to be the population proportion? P-hat. So again, in this one, we have population versus sample. We have your population mean, we have your sample mean. These guys are point estimates. We have your proportion, we have your p-hat. We have your standard deviation, we have your sample standard deviation. We have your variance, we have your sample variance. Okay, so these in your sample are your point estimates. It really basically means the same thing. Find me the mean, find me the proportion, find me the standard deviation. So we find out of 30, and here's again greater than or equal to 30, this is a z-score. We find your point estimate by putting it in your L1, find one bare stat. L1, we have no frequency, so make sure the frequency is open, it's not there, and calculate. Find your mean and your sample standard deviation. We do the SX because this is a sample of 30. There means there's more dishwashers in our population. So this is a sample of 30. Find your mean, and that's your point estimate. Your margin of error, you have a nice little formula for a z-score margin of error. You need the critical value for your z-score. So we need to know what our level of confidence is. And I think I give you these as well, basically, most of them. But if we were going to find this ZC, remember how we did this? This is important in case it's not on your chart. 95% fell in the middle. This is your 1 minus guy, divide by 2. How much is left to share in the tails? 2.5, right? 5%. So you're going to take your 5% divided by 2. Okay? I want to know what my tail is. This is at negative 1.96. This is at positive 1.96. All I want is the positive number. The margin of error, it should be a positive. We use a plus or minus. So even if you did the negative, you're still going to end up with a negative of a negative. You'll end up with a positive. So we fill in your standard deviation, which we found in your calculator, divided by the square root of how many was in your sample, and we find your margin of error. Remember, when we build your confidence interval, it's the mean plus or minus the margin of error. So once we do that, we just add and subtract your margin of error. And you need to remember how to say this. You will be 95% confident that your population mean for these dishwasher repair costs will fall between $89.26 and $106.96. Not your sample. It's not 95% of your sample. It's not your sample falling in there. You know your sample falls in there. You made this be right in the middle when you did this, x plus or minus e. You're doing this to give an inference about your population. So make sure that you remember how to say that. You are 95% confident that your population mean repair cost will fall between those two values. This is key. I need this word population in here. This is why we do a point estimate. Agree? This is our confidence intervals. We spent a lot of time going through chapter 6. We did it for the mean, we did it for your t-scores, we did it for your proportions, we did it for your standard deviations. But they all work the same. The mean, the proportion, standard deviation, plus or minus 8. You can also use your calculator, and I'm not adverse to you using your calculator on your final as long as you tell me. Now remember, when you look this up, this is a Z interval. Usually what gives this away is if you look up the wrong thing, it doesn't have for you to say C in there. So you need to be able to say the C. What's my level of confidence? Like a hypothesis test needs your tail in there. So you can pretty much see if you did the wrong one. So remember, this always has to have the C value in here. You have to state your level of confidence. And remember how I showed you when you get your interval? If you take your interval and you subtract out your mean, the answer will be your margin of error. So if you use your calculator and do a Z interval, and you get your interval, subtract out your mean, and you get your margin of error. You're fine using your calculator on this as well. The one thing though, don't ask me how to use the calculator. If you don't know how to use it, you have to use the formulas. And the calculators practice it. They're nice to use. The sample size was always tricky to you guys. Determine the sample size. I give you the sample size. We have a sample size for this and for proportions. We don't have one for the T. Again, it's finding your Z-score, your critical value for your 99% in this case. We take 99% out of the middle, we share 0.01, inverse norm, 0.01 divided by 2. That's your ZC. That's this guy. Times your standard deviation, and we give you your margin of error. Whenever it says within, that's your plus or minus, that's your margin of error. You plug it in, figure it out, don't forget to square it all, and always round up. Round up. If you cut it off, that means you never got to that point. If you wanted 33.5 people for dishwashers, and you cut it to 33, you never hit 33.5. So you always have to round up to make sure you hit that.
Is rounding off always in sample size though?
In sample size, always. Questions on this? This is a good one to review. It's been a little while since we did confidence intervals. Okay. And those of you that use a calc, try it again on your calc. Let's hit one more, 21. The following represents time in minutes. Now, we notice this sample size is small. T is your sample size. It's still a sample. And count how many are in your sample. You have 10 in your sample. Again, you're going to put it in your L1. You're going to pull out your standard deviation and you're going to pull out your mean. Standard deviation. Okay. But now, you're going to use a T because n is less than 30. And you're going to construct a 90% same way, but your T cutoff comes from your table 5. Remember doing this for table 5?
Yeah.
You have your degrees of freedom. You have your level of confidence on the top. Your table 5 gives you 3 rows across the top. Level of confidence is all by itself. Then you had a 1 tail and your 2 tails. That was for your hypothesis test. So, A good 2-point question is finding your cutoff value for this. Be able to read table 5. Degrees of freedom, across the very top is your level of confidence. Find your 90%, find your degrees of freedom, and you will find your critical value. The rest pretty much fits in the same way. Standard deviation over the square root of n, and then you build it the same exact way. And if you use your calculator, it's t interval. T interval automatically finds everything else for you. The ZC, the TC, the ZC, everything is found in your calculator, by your calculator. The only thing it doesn't give you is margin of error, and you just have to subtract it from your higher end. Any questions?
There's another, I think there's D.
There's a B?
There's a part D.
Oh, there's a part D. I'm sorry. Okay. Okay. Oh, very good. This is a good one. This compares your Z to your T. If I know my standard deviation from my population, I automatically use a Z-score, regardless of the size. So I do this again, and the only thing that's changing is this guy right here. Notice the difference? I'm just multiplying by a smaller number. In your T, I multiplied by a larger number. Therefore, your T has a wider interval.
More wiggle room.
More wiggle room. Good. It has a larger margin of error. It gives you a wider interval, a little more wiggle room to work with. Because the T says, I don't really have enough in my sample, and I don't know anything about my population standard deviation, so give me a little bit more wiggle room in here, in case I'm off. Part B says, you know your previous standard deviation from your population. You don't need to be as exact. So,
How do you get 1.6?
the regular way, you take, what was this, 95, 90%, 90, and they share 10. You have to do an inverse norm for this. I should have a table there, and that's on your Z chart. If you look at your table 4, look at your table 4. You have the basic Z-scores down here. 4 gives you like the normal ones, the 90, the 95, the 99. See your ZCs for those? So even if you forget how to do it, you could practice with one of those to make sure you get it right. Okay, tomorrow, guys, we'll finish this up.